we'll see if I do anything with this recording or not. Okay, so if if any competition models in ecology, it's going to be the Lotka-Volterra competition model. It's the one that more or less every undergrad who goes through ecology sees. And I saw from the poll, like everyone's seen it at least once. It goes back to these fellows who were working in the 1920s. And they were working kind of in parallel on different, different continents. And they couldn't be more different. Okay. So Vito Volterra, one of the leading mathematicians of the era, got into ecological problems because his son-in-law was a fisheries biologist, and he would like pose problems to him at the dinner table, and Volterra would be like, "Yeah, okay, let's see what I can do here." Locke, on the other hand, was a bit of a scientific outsider. So he started, got his degrees in, I think, physical chemistry, and then he kind of like dropped out of academia. So he's the original alt-ac kind of person. So for a while, he was a scientific editor for Scientific American. He essentially is kind of like a scientific blogger of the day. So I just give you this classic article from 1919 on the high price of milk. But then Locke got a job at the Metropolitan Life Insurance Company in New York. So he applied his demographic skills to like figuring out how much to charge people for insurance. So yeah, it was a little bit of I guess, a rivalry between the two, but maybe it was a little bit one-sided because Volterra probably didn't care too much. Locke was very concerned about making sure that his contributions were acknowledged. If you want to read more about it, there's a book here on the history of population ecology by Sharon Kingsland, which is really nice read. And I'll like send these slides around somehow too, so I don't feel like you have to take notes if you don't want. Okay, so what is this Lotka-Volterra competition model? The first thing we're going to do, the jumping off point, is logistic growth equation, which I'm sure you all know, which has two parameters: intrinsic growth rate, little r, and carrying capacities, big K. And we've got a version of these equations for each species, right? Hence the subscripts on everything. So the logistic part handles that, incorporates the intraspecific competition, density dependence, same thing. But we're gonna need to add some stuff, because right now, if we stopped here, this would be like two non-interacting species, right? Which is, probably relevant a lot of times, but not what we want to talk about. So first thing we want to add in here is we want to add an extra term to each equation for interspecific competition. So this is modeling the effect of species 2 on the per capita growth rate of species 1 and vice versa. But we're not done yet. We got one more ingredient in here, because right now as written, it kind of assumes that interspecific competition, intraspecific competition, they're equal in strength, but in general, they may not be. So we want to add some competition coefficients, some more parameters that are going to scale the relative strength of intra and interspecific competition. Yeah, you could unprop it if you want, and just let some like Stanfordites in. Maybe. Yeah.
Okay, well, you'll post it when you're done.
Yeah. All right. So this is it. This is the traditional, let's call it RK form of the Lotka-Volterra competition model. And it's got 6 parameters for 2 species. It's a dynamic model, forgot to mention that. So it talks about how, how do we read this? On the left-hand side for each equation, we got the change in population 1 with respect to time. And on the right, we just put all the processes, the terms that we think cause species N1's abundance to change over time. Any questions? A quick reminder of this thing? All right. So this is the traditional form you find in textbooks a lot, but there are a couple different forms that people use for it. They're equivalent, but the parameters have slightly different meaning. So here's another one. This is the one that I'm going to use today for kind of inexplicable reasons, which we can call the R alpha form. And so here we don't explicitly have the carrying capacity as a parameter, but now we've just got like these 4 competition coefficients. It's a little bit more elegant, a little bit more symmetric like this. And we can back calculate if we want to know what is the carrying capacity of species 1. It's just its growth rate Ri divided by alpha II. Why use this form? There's a paper by Jim Mallett, 2012. It's like 30, 40 pages long. And it's all about different forms of logistic equation and by extension, Lotka-Volterra competition equations. Like how can you write a 30 or 40 page paper on that topic? But it's really good, super interesting. Check it out. So one of the advantages of this form over this one is a little bit weird in 2 ways. So one way that this one is a little bit weird is if the intrinsic growth rates are negative, that is, if a species is kind of outside its fundamental niche, then in fact, then having competitors around makes you grow faster because you're multiplying a minus by a minus. And that can lead to some weird behavior. So this is a little bit problematic if the R's are negative. The other thing that's a little bit weird about this one is you'd think that if you grow faster, you think if your growth rate little r is higher, that should like make you a better competitor, should increase your carrying capacity, should do something good for you besides make you grow faster. But here the little r is factored out, and that's all it does is makes you grow faster. So this is some of the downsides of this form. So we're going to use this one. The main reason I decided to use this one today is because the paper we'll read for next week is built on this form. I thought it'd be a little bit less confusing. So, okay. Any questions out there on the setup?
So you said the negative things about the previous one, but so that just means so it's mainly just 2 things, and it's that there's a problem with the intrinsic growth rate, and then the second one was just that you said that like there was also a problem with just the way R is being used in the equation itself.
Yeah, I mean they're not insurmountable problems. I wouldn't use this one if little r was negative. Let's put it that way, because that's going to be like weird. Because then like instead of competition, it becomes mutualism, and you don't really want that. The other thing that's slightly weird, but like whatever, maybe it's just an assumption, is here in this formulation, the little r's, they don't really affect the long-term outcome at all. All they do is like set the speed each species is moving at, which, maybe that's the case, but this one doesn't have those. So.
Okay, thank you.
So
Yeah, Matt.
yeah, so my question is the interpretation of little r, does it change between these 2 formulations? Because one of the things that I guess, because I guess another way you could write AII, right, is RI divided by K, right?
Yeah.
And so I guess what I'm wondering is like, I know sometimes in like some stability analysis, you might perturb R, but then are you accounting for that if you use the A, like this formulation of the, does that make sense?
Yeah, I think so. Well, so one thing about, I think the main interpretation of the little r's is the same here, which is that if both species were rare, if we got rid of like any kind of competition intra-specific, little r would be their growth rate in an empty environment, and that would be true for both. So you don't have to worry about that. I mean, the alphas are definitely like have slightly different interpretations between the 2.
Right.
And it's just I mean, it's just a matter of taste, and you just have to like pay attention more or less. And some things are better for some uses. It's just
Okay.
something to be like careful with. And yeah, and there's like some other ones. It can be a headache if you're trying to convert between them.
Yeah, gotcha.
All right. Any other questions on this thing? All right. So, okay, so how are we gonna analyze this? So this is traditional. This is like the original competition model in ecology. So we're gonna, we can study it for like historical reasons. We can also study it for pedagogical reasons, which we'll see. But people still use it today. I mean, it's still like, in circulation. New things are being discovered about it still, 100 years after it was invented. So it's just a matter of taste. I think, if you have if you need a competition model and you don't want to make any like particular assumptions, particularly special system specific assumptions, go on and use Lotka-Volterra. Okay. But of course, most of the class will be not using this thing. So anyhow, so how are we gonna analyze it? So one of the reasons it's been popular in theoretical ecology is because you can analyze it really easily with this so-called phase plane analysis. And it's kind of a graphical approach. Ecologists like graphical approaches. So we'll walk through that. But the idea is this. We're gonna work in this N1, N2 phase plane. And any point in this plane describes the current state of the system, right? So it tells you how many N1s and N2s you have at any given point in time. And what we're going to do then is we're going to say, like, for any given combination of N1s and N2s, how are they going to change? So they're going to each go up or go down. And we'll use this to build up kind of this graphical approach to understanding competition. I mean, it's pretty amazing, how much you can figure out just with pencil and paper on this thing. Okay, so the first ingredient we're going to need in this analysis are what are called isoclines. So isoclines are a set of N1s and N2s where a given one species stops changing. Okay, so we take its time derivative, set it equal to 0, and then we solve for that and plot it in this phase plane. So for species N1, it stops changing due to, it could happen in two ways. Either N1 equals 0, which means you forgot to add the N1 to your experiment. And if they're not there, we're assuming it's a closed system. And so it'll stay like that forever. Alternatively, this stuff in parentheses could equal 0. This stuff in parentheses we can interpret as the per capita growth rate, the sort of realized per capita growth rate of our species N1. So on the N1 isocline, it's got two parts. Either N1 equals 0 or this other stuff equals 0, which, you can rearrange it and you see it's a straight line with negative slope. Right? Don't forget about this N1 equals 0 part. It's pretty important. Serves a good purpose here, which is it's gonna like, together with the N2 isocline, it's gonna make like a little fence. It's gonna make a fence so that the state of the system always stays in the positive quadrant. So we don't have to worry about species getting into negative land, doing unrealistic stuff. Okay, so that's the N1 isocline where N1 stops changing. Next thing you want to do is add some little arrows to say like how species N1 changes at any point that's not on an isocline. Okay, and since N1 is on the x-axis, we either go left or right here. And, pretty simple if like you're at low density, feeling good, not a lot of competition. See, N1 grows, but up here, if both species are abundant, then N1 shrinks. So we can just kind of like logic our way through figuring out which way those arrows go. Any questions, N1? Isocline? All right, same logic applies to N2. It's got an isocline that's either N2 equals 0 or some other line with negative slope. And instead of going up, left and right, it goes up or down. Okay, so this is dealing with the two species in isolation to figure out what happens when they interact through competition. And we just superimpose these, put it together, and we can sort it out. So yeah, so what we're gonna do is we're gonna put these two isoclines together. we can, at any given point, we can add up those vectors and point at, we either just quantitatively and make it actually go in exactly the right direction, or we can be just kind of approximate and just the general like northeast, northwest, southeast kind of deal here. In any given region of this phase plane that's, you know, within some isoclines, they're all going to go the basic same direction, right? So every point in this lower triangle is going to go to the upper right. Every point in this strip in the middle is going to go down to the right, and so on. So then isoclines are where one species stops changing. What we're really going to focus on a lot are equilibria. So an equilibrium is a state of the system where no one changes. Both species don't change. And so in our graphical approach, we find equilibria by looking at the intersections of the two different kinds of isoclines. So we need two different colors to cross here. So there, in this particular example, there are three equilibria. There's the so-called trivial equilibrium, 0, 0, everyone's dead. There's this one over here, which is species 1 by itself. And this one over here, species 2 by itself. Just don't get tricked, like this point up here, that's not an equilibrium because it's just two parts of the species 1 isocline that come together. Not too important. Okay. And so then, based on this picture, we can kind of imagine how the state of the system changes. So if we started out down here with both species at low density, they're both going to grow up. Species 2 is going to peak and start coming down while 1 keeps growing. And we're going to get sucked into this equilibrium point where it's just species 1. Okay. So equilibria, that's what happens. That's, you know, a good candidate for what might happen in the long term. But not all equilibria are created equally because we have to worry about their stability. Stability means equilibrium points can be stable if we start there, perturb the system away a little bit. If we come back, it's stable. And we can tell that this equilibrium point is stable because all the arrows are pointing right at it. Whereas this one over here, species 2 by itself, this equilibrium point is not stable because if we sprinkle in some species 1 can grow, this arrow is pointing away, we're going to run away from that point. Therefore, these two equilibria are unstable. So in the long term, stable equilibria are kind of like a likely place we're going to find our system. Long term meaning time goes infinity, which is kind of the standard approach in theoretical ecology. All right, so any questions on how we do this kind of handwritten phase plane analysis? All right, so the important part of these isoclines, they're lines with negative slope. Turns out there are 5 different ways we can get two lines to intersect, to cross or relate to each other. And so each one of those 5 ways is going to be one of the cases of Lotka-Volterra competition, one of the outcomes. So what are these 5 cases of Lotka-Volterra competition? All right, so the first one we just saw. So this is the case where species 1 outcompetes species 2, which means there are 3 equilibria, and in long term, only one of them is stable. It's species 1 at its carrying capacity. And so in long term, we only expect species 1. And we can characterize, we know we're in this case just based on the intercepts of these isoclines and how they arrange relative to each other. So here, R1 over alpha 1, 1 is larger than R2 over alpha 2, 1. That's our first inequality. Our second inequality we get from the points on the y-axis. So that's how we can kind of determine, you know, a priori which of these cases we're in. Case 2 is just the same thing, but like flip the axes. Not so exciting. Now, in both these cases, the isoclines didn't cross in the positive quadrant. So there's no chance of coexistence here. It's just going to be competitive exclusion. Just have to see who's better. But another possibility is maybe they cross. Maybe they cross in the positive quadrant. And so in this case, they cross, and all the little flow arrows are pointing right at this new coexistence equilibrium. This is the case of stable coexistence between species 1 and 2. We've got 4 relevant equilibria. The only stable one is this one in the center. And again, we can figure out the conditions based on the points on the intercepts. Okay. So this one is the next one is the one that maybe people find surprising the first time they see it. We could also have these 2 isoclines intersect, but flip the order. And if we flip the order, we're going to flip the direction of some of those arrows. Okay. So this 4th case of Lotka-Volterra is what we call founder control. And what that means is like, look at it. So now the coexistence equilibrium point is unstable, but the 2 monoculture equilibria are stable. So these are, first example of where there's multiple possible attractors here. Either species 1 wins or species 2 wins. What you end up on is going to depend on the initial conditions. Right? So this is an example where history matters. All right. So this is like the evil twin of stable coexistence. So these are the classic, I would say, 4 cases that everyone talks about in Lotka-Volterra competition. Any question on those?
Just, yeah, one quick question, Chris, just to clarify, would this founder control, like in other words, would be a priority effect?
Yeah, that's another name for it.
Yeah.
Uh-huh.
Okay.
Thanks.
Gotcha. Just one.
Question in the chat. What's the first case again? The first case was just species 1 wins. All right, so these are the 4 textbook cases of Lotka-Volterra competition, but there's one more. People don't talk about it a lot because it's a little bit weird. It's a little bit degenerate. It's a borderline case in a lot of senses. But anyhow, it's an important one because the whole like ecology in the 2000s was devoted to this topic, which is the so-called neutral theory. So the idea of neutral competition is essentially the 2 species are interchangeable. You can't tell that, they have identical effects on each other. And when that's the case, then their isoclines completely overlap. And then the stability analysis gets weird. So here there's an equilibrium at 0, which is unstable. But then we have this whole weird degenerate line of equilibria. And if we do stability analysis on them, we see that in this direction, that line is stable. But then so in the direction of total biomass or total abundance, it's stable. But in this direction of like relative abundance, N1 versus N2, it's just flat, a flat landscape. So wherever you start, you're just going to stay there. Okay. So anyway, I just mentioned this because it's like this weird borderline case, but also because, Steve Hubble in the 2000s, got everyone thinking this might be the, key to understanding diversity in real systems. He added some extra ingredients, it wasn't just this. He added dispersal and stochasticity. But this is like the most neutral model possible. All right.
So
yeah, go on.
Chris, just really quick, would you get that if you in the RK form, if you dropped those competition coefficients?
Yeah, I mean, all the outcomes are, you can get all the outcomes. It's just slightly different forms for them.
Yeah.
I have a question on this one last case that I've never heard about before. So what is the pro of using this? Because it seems to me a lot like you are modeling the same species that competes with itself. So first, I want to check whether this is true or not. And in this case, what is the like why would I decide to use this instead of one species model or another and this two species model?
Sure. Yeah, I mean, in this case, yeah, I mean, basically the two species are identical. So maybe they're, maybe they're sister taxa that like, recently diverged. They're totally ecologically equivalent. Maybe they've got some like, neutral markers that like you can tell the difference between them. But when it comes to competition, they're the same.
But when you say they're the same, it means those parameters equal each other. It
Yeah.
doesn't have to be like R1 doesn't have to be exactly R2, for example.
No, but that's the easiest way. The easiest way to make it is like just make all the parameters equal. You could come up with a neutral case by like carefully balancing the R's and alphas as well.
Right.
But usually when people talk about it, it's just like individuals are interchangeable. Yeah, I mean, it flies in the face of what interests ecologists in a lot of natural history, where we study how species differ and their adaptations to the environment and so on. So that's why it was pretty radical in 2000-ish when Steve Hubble proposed the whole theory of biodiversity based on this pretty obviously bogus assumption. I think I don't know what he was doing. He just wanted to see how far you could get with that. I think at the same time, there's an argument to be made, and people have made the argument that, well, okay, the arguments always go back and forth in a very standard way on this. It's like, this is a weird borderline case. It requires the parameters to be completely equal. What are the odds that these parameters are exactly equal? Probability 0, therefore we're going to ignore this. Then the counter argument is that maybe natural selection pushes species to be identical. So if there's like a single best way to be adapted in a given environment, then everyone just evolves to be the same and they're neutral. I mean, I don't want to defend it. I'm just putting it out there, just so you can see like where the whole like Hubble's neutral theory, like what's underlying it. It's this case 0 of Lotka-Volterra.
But is it possible that they evolve to be equal, like equal in this system, but then in another, like not all the parameters are the same, but then you change to another system, they like become different, that their fitness will be.
Yeah. That's
That's
kind of philosophical. Yeah.
It won't be called neutrality in this case.
I mean, I guess it would be neutral in the case where they're equal and otherwise not. Anyway, I don't want to dwell on this one too much just because it's kind of weird, but just tossing out there for context. Okay. So that's what you can do with just pencil and paper and what Lotka-Volterra did in the 1920s. Any more questions on these possible cases, outcomes? All right, well, I want to like show you a little bit more like the details of how you can do this analysis mathematically, because you can only get so far drawing like isoclines and arrows on paper. So this is going to be the same thing, but now from a slightly more rigorous mathematical perspective. And this is going to be kind of general for two species interactions. Actually, it's going to be general for any species interactions. This is how you do kind of equilibrium analysis in ecology. So the first thing you do is and I should say this is for continuous time models. It's a little bit different in discrete time. So, okay, so to find equilibria, you set the dn dt for each species equal to 0, and you simultaneously solve them for the equilibrium values n1 and n2. This is just like the algebraic version of like finding where those different kinds of isoclines cross. All right. Here the F1 is like going to be shorthand for the right-hand side of dn1 dt. Okay. And so basically this is a good trick because we started with differential equations, but then we got rid of the time changing part, and then we converted it to a system of algebraic equations, which is a lot easier to deal with. So that's why this works. This is how we find equilibrium. And sometimes you can do this in closed form with algebra. Sometimes you have to do it numerically. Lotka-Volterra, it's really easy. But then remember, the other thing is not only equilibria, we have to check their stability. So to do that, we're going to use this thing called linear stability analysis. And again, like we did in the picture, imagine we start out at an equilibrium point and then nudge it a little bit. We do apply a small perturbation. And we want to know, is that perturbation going to grow? If so, then that equilibrium point's unstable. If the perturbation dies off, the system returns to its former equilibrium, then we say that equilibrium point is stable. All right, so mathematically, the way you do it is you make this thing called a Jacobian matrix. It's a matrix with all the combinations of partial derivatives of, the growth rate, F1, F2, versus all the combinations of the species abundances. So this upper left entry is saying, like, how does the dN1 dt change if you add a little bit of N1? This in the upper right, how does the rate of change of species 1 change if you add in a little bit of N2, and so on. So we got all the combinations, we're going to stick them in a matrix, and then we're going to evaluate this Jacobian matrix at the equilibrium point that we're interested in. And then we got this kind of concrete matrix in our hands. We need to convert into something a little bit simpler, some numbers. So we calculate its eigenvalues. Okay. And I can send you some links if anyone wants to learn more about eigenvalues, don't know them. But suffice it to say, if you have a n by n matrix, it's going to have n eigenvalues. And here are the rules. The rules of linear stability analysis. An equilibrium point is stable, linearly stable, locally stable, if all of its eigenvalues have negative real part. If there are any eigenvalues that have any positive real part, that equilibrium point is going to be unstable. That's the main rule. And then finally, the last rule is kind of the like fall through edge case. If the largest eigenvalue has 0 real part, then linear stability analysis fails. Maybe it's neutral. Yeah, you have to check a little bit harder in that case. But this is only a weird borderline case. You don't really run into this a lot. Okay, so this is, we'll go through in Mathematica how to do this stuff too. So it's just like the first general theoretical iteration of this, and then you'll see it in practice. But any question on like the sort of mathematical theory on that? All right, so that's the general approach. Sometimes when you do this, it's kind of gets ugly fast. Those eigenvalues, they're terrible algebraic expressions often. So here's a little shortcut. Here's a little hack that we can use, particularly in competition models, which is pretty much one of the greatest tricks ever invented. So this is the idea of invasion analysis. So the idea of invasion analysis is consider each species by itself with the other one absent. If you sprinkle in the second one, the invader, can it grow when rare? Can it rebound from rarity? Can it invade the system? And so we calculate that with these per capita growth rates. We're taking, this is the growth rate, invasion rate of species I invading a monoculture of species J. We take species I's per capita growth rate, so dN I dt, but then we got to divide by Ni, make it into the per capita rate. And then we evaluate that at the equilibrium point where it's just species J at its carrying capacity and species I is essentially absent. So the reason why we focus on per capita rates, why do we have this 1 over n here, is because if we were to evaluate just dN I dt when Ni equals 0, it's going to be 0 because it's not there. So we have to like cancel that out essentially. So that's the point, is that this species is rare. So rare that like no one knows it's there yet. Has no effect on anyone, doesn't have any effect on itself, doesn't affect the resident species, but the resident has an effect on it. So it kind of like decouples competition. And this is like the simplest case. For more complicated models, there are other ways you can calculate this invasion rate. We'll probably talk about later. And the same rules apply. So what are the rules? So the rules are if species 1 can invade 2, but 2 can't invade 1, then we say 1 beats 2. Vice versa, 2 beats 1. Here's the one that most exciting. If each species has a positive per capita growth rate when rare, invading a monoculture or the other, their invasion rates are both positive, then we say we're in this case of stable coexistence. In this particular test, we can call it mutual invasibility. And finally, if we're in the situation where neither one can invade a monoculture or the other, then we're in the Lotka-Volterra founder control case. So this is invasion analysis. It makes the math a lot easier. Yeah, you got a question there, Sarah?
Yeah, hi. It's concerning the third case where it leads to coexistence, but so just to be sure, it's because it relies on them being rare. So we have to consider that with time, this will change. It's only true for a small amount of time, no matter the unit or something. It's not stable as it is in a system.
Yeah, I would say that basically it's kind of like, it's kind of like their insurance policy. If, a particular species ever like had a string of bad luck and became rare, it could come back from that, right? So yeah, I mean, that's the beauty of it, is you don't really care what happens in the interior of that phase plane. You're only talking about what's happening on the border with invasion analysis.
Okay, right. Yeah, I see. Thanks.
Yeah, so this paper by Tess Granger et al. Kind of gives people, try and popularize the invasion analysis. You can also do experiments like that. Hans Metz et al. Had a paper kind of like esoteric, showing how this can be generalized to more complex scenarios. But it's not. Oh, yeah, John?
Maybe this is just what you're referencing, but I was wondering, like, does something like this work for like N species? Like, if I have like 1 outcompetes 2 and 2 outcompetes 3, or if 1 outcompetes 2 and 2 outcompetes 3, does 1 outcompete 3, stuff like that.
Yeah. There are issues. I'll get into those issues on the next slide, and that is one of the issues. These rules are perfect for Lotka-Volterra, 2-species Lotka-Volterra competition. Like, this is totally correct, but there are a few ways that this can go wrong. So what are the ways it can go wrong? So here's one way. Basically, in both senses, you can make examples where invasion doesn't mean a species is going to persist, and you can make cases where a species can't invade, but maybe it could coexist. All right, so this first example here is what you can call unprotected coexistence. And the isoclines are all bent around, so it's obviously not Lotka-Volterra. There are a lot more equilibria. Basically, in this case, each species has an LE effect, so that it's got a minimum viable population size. So now you can see that, yes, there's a stable 2-species coexistence point, but then the monocultures are also stable. So this would be a case where neither one could invade each other, but there's still, for the right initial conditions, you could get the 2 to coexist. This is one way it can go wrong. Sort of the converse is in more complicated models. You can have a situation where a species initially starts to invade, but then it goes extinct later on. This is in a perfect deterministic world, no demographic stochasticity. And as John was alluding to, it's not completely sorted out how to do this if you have more than 2 species, because maybe if you have, say, 3 species, then maybe all the 2 species coexistence points don't even exist. So what are you going to do? So anyway, these are issues with invasion analysis. Good to keep in mind. None of this actually like worries me. I just go on and use it and just pay attention to like when these possibilities might rear their ugly heads, but they usually don't. Yeah, Matt?
Chris, does this also work? Like, let's say you're interested in like coexistence of two species in like a diamond, like food web, like module, but you just like ignore the resource and ignore the predator. Can you also like this invasion criteria?
Yeah.
Does that also
Yeah.
work? Okay.
Yeah, we'll get to that example at some point, and we'll do it at that point. So it's pretty general. It's a pretty good technique. Some people like really want to completely like chuck it because of these problems, but it's we only have so many techniques that actually work, so might as well like hang on to the ones that mostly do, my opinion. Okay, so that's the idea of invasion analysis. Oh yeah, and the good thing about it is it's a lot easier to calculate, right? So we'll get into that right now. So I'm gonna pop over to Mathematica and just like show you like how we can, yes, Mathematica examples. So just rearrange my windows. Sure. All right, well, I tested this morning, but hopefully it'll work out okay. So this is Mathematica. If you haven't used it, it has this notebook-like interface. Everything I've been spending a lot of time working on a package to help out with analyzing ecological models. So I'm going to use that extensively. To install it, you just do this once. You just do it once ever, and it's like installed on your computer now. So I'm not going to run that because I hopefully have it already installed. But then I'm just going to get into the cell. Sorry for people that use Mathematica. There are these cells that like hold a chunk of code. And when you click in there and hit shift return, then you're like saying, hey, run that chunk of code. And so you see that it has this in one, out one. This is kind of like the input and output from that particular chunk. And so this first bit here is just loading up my package so we can use it right now. And the second thing we need to do with my package is we have to sort of like install a model. You have to say, this is the model we're going to be working on. And once we do that, this is what we're going to be working on until we set a new model. The good thing then is we don't have to like be retyping these equations all the time. So here we're just saying there are two populations. Here's the right-hand side of their differential equations. This is optional, but we can give it a list of what are parameters of the system, and we could also give it some restrictions on them if we want, some ranges. That might help later on and like help simplify algebra for us. Not required. Okay, so once we've done this, now this model, Lotka-Volterra Competition model is installed, and we can go on and analyze it. So first thing we want to do is solve for equilibria. And so that's a solve eco-eq. And essentially behind the scenes, it's taking the dn dt for each species, setting it equal to 0 and solving it algebraically for us. And it returns the solution in the form of this list, because there's, in general, going to be 4 of them. 0, 0, trivial equilibrium, species 1 by itself, species 2 by itself, and then this potential coexistence equilibrium. Yeah, Jonas?
Yeah, just quickly, as I don't remember, does your package automatically discard any negative solutions for populations?
No. And so at this point, actually, we haven't like laid in any parameter values, so it doesn't even know like what's positive, what's negative. Later on, once we've put in some parameter values, it'll still happily report negative equilibrium, but we can like throw them out using some select valid. So that's an easy way to throw out ones that are negative. So yeah, if anyone has any questions along the way, just feel free to jump in here. Okay, so we have these, oh yeah, the other thing I should point out, this is just mathematics and syntax, but basically all our results are going to be in the form of these, what we can call rule lists, where it's like a variable arrow and then the right-hand side. We can use these later on to like substitute in or as inputs for some other functions. But okay, so here's the four equilibria. We can calculate the Jacobian matrix with this eco-Jacobian. And you can see it's this 2x2 matrix with a bunch of partial derivatives in it. And then we can calculate the eigenvalues using eco-eigenvalues. And so it's automatically going to be calling this Jacobian behind the scenes for you. And we can do it for each one of these four equilibria one at a time. So here we're saying, give me the first part of that list of equilibria and what are its eigenvalues. Okay, these are simple, R1, R2. So this is the trivial equilibrium. The eigenvalues are just the intrinsic growth rate of each species. If we assume that those are positive, so that species can even live, then this is going to be unstable, right? Because they're going to be positive. Equilibria 2 and 3, that's the two monocultures. They each have two eigenvalues, one of which is negative if we assume little r's are positive. So we don't have to worry about this one. This other one, we don't know. Is that positive? Is it negative? Is it going to be stable or is it going to be unstable? Depends on the sign of this dominant eigenvalue. If we were to rearrange that, then we would essentially get the conditions for, if we rearrange both these, we get the conditions for coexistence that we looked at earlier. And finally, the coexistence equilibrium point, is it stable or not? We can look at its eigenvalues. Well, this is where it starts to get ugly, right? This is already like the simplest possible competition model. And now we have to figure out this thing has negative or positive real part, quadratic equation. It's already kind of horrible. So this is kind of like just to say like, this is why we like invasion analysis. So we don't have to deal with this thing. Finally, we can also just ask if each equilibrium point is stable or not. And right, I mean, this is why Mathematica is handy, because I don't trust myself to do all this algebra and get it right. And so it's going to like calculate, under what conditions this equilibrium point is stable or not. And in the first one, because we've already hard coded in that the little r's are positive, and it's just like, nope, ain't stable, false. These other ones give the conditions, right? So there's a condition for the species 1 by itself, species 2 by itself, and the condition for species 3. Here I use this full simplify. I bet it could be made even simpler than this, but it helps. All right, and then finally, while we're doing this, so it's all like kind of like we haven't laid in any parameter values yet. We're just doing this kind of generic sense. So the last thing we can do is calculate those invasion rates that I was telling you about for the mutual invasion test. And we use this function INV for that. And we say, this is saying, what's the invasion rate of species N2 trying to invade equilibrium 2, which was species 1 by itself, and vice versa. So these are the invasion rates that we could use for invasion analysis. All right, so this is, we're kind of like, this is the end of algebra, I guess. Any questions on the implementation or just the general concept? Yeah.
To the perturbation. So when you define whether a coexistence is stable, you said in that figure you perturb a little, but then the invasion is different from that, because if it's a stable coexistence, both species have relatively high abundance. In that case, a little perturbation would mean both species are not rare. But then invasion, I guess it's coming back to the slides you said when the model doesn't work when it has a problem.
Yeah.
Because then you, like in that figure, you have problem, you perturb a little, it can come back. But then if you let one species invade when it's very rare, it cannot come back.
Yeah.
So I guess what I'm question is like the invasion test is not exactly the same as if you solve the
Yeah.
lot of the.
Yeah, well, let me just let me see if I have one of these. So let's look at this one. Okay, so in fact, the invasion analysis is a shortcut to doing some linear stability analysis. But what it's doing is it's basically testing the linear stability of the boundary equilibria. So one invasion rate of 2 invading 1 is like, is this little arrow pointing up or is it pointing down? And then the invasion rate of 1 into 2 equilibrium is this arrow pointing to the right or is it pointing to the left? So in fact, it is a shortcut to doing linear stability analysis, but on the boundary here, and you're right, you know, this coexistence equilibrium point, we're not really saying if it's stable or not based on this because we have no way of knowing because it's way over here and it's like outside the range of our small perturbation. So with invasion analysis, it is small perturbations, but small perturbation around these equilibria on the border, basically. So. All right, any other general questions?
There's something in the chat.
Oh yeah. So Wu's asking, what's the difference between simplify and full simplify? It's just like how hard mathematics is going to work and try and simplify it. How many like tricks it uses. It's a little bit slower, but a little bit more effective. Maybe use full simplify. All right. So yeah, this top part is why I like Mathematica because it can do algebra, unlike our little r. Okay, but now let's get into some numerical examples. So let's look at the 5 cases of Lotka-Volterra. Excuse me. So now we're gonna like lay in some parameter values. We're gonna assign numbers to little r's and the alphas. So now when we run everything, instead of getting algebraic expressions out, we're gonna get numbers out. So when we solve for equilibria, we see that there's 3 of them. In this case, the trivial equilibrium, species 1 by itself, species 2 by itself. We can calculate their eigenvalues now numerically. And this numbered grid form is just an easy way to line them up so we can actually read what's going on here. So there are 3 equilibria. The trivial equilibrium, its eigenvalues are 1.2 and 1. Those are both positive, therefore it's unstable. This one, species 1 by itself, both its eigenvalues are negative, therefore it's stable. And then this last one, species 2 by itself, it's got 1 negative, but 1 positive eigenvalue, therefore it's unstable. Okay, so this is what we expect. This is numerically calculating the invasion rates. 2 into 1, 1 into 2. One's positive, one's negative, so we know that we're in the competitive exclusion case. Also, just to point out, you know, like we were just talking with Shen, this invasion rate of species 1 trying to break into species 2 equilibrium is literally the same as this eigenvalue here. So this 0.2 and this 0.2, they're the same thing. And this negative 0.2 is the same as this negative 0.2 down here, which is 2 trying to break in and invade species 1. So that all lines up. This plot eco-phase plane then will plot the phase plane, but instead of like little, you know, hand-drawn arrows that are kind of approximate, it puts the real arrows in for you and also identifies the equilibria and with little circles, as well as their stability. The stability is kind of like this is just the graphical, you know, way we write it is open dot means unstable, filled dot typically means stable equilibrium point. And we can see that this species 1 equilibrium is stable because all the little gray arrows are pointing towards it. So that all lines up. Finally,
Hey,
we
Chris?
could, yeah.
Oh, sorry, quick question. So the arrows, so basically it's calculating the sum between N1 and N2 at like these like millions of locations within the graph.
Yeah, I mean, it's evaluating like dn1 dt and dn2 dt at a bunch of points on the graph, and it's kind of like making a nice little, yeah, it's drawing nice arrows for us.
Interesting. Thanks.
Yeah. Yeah, I mean, back in the day, like Lotka and Volterra didn't have this, so they were probably just drawing the arrows by hand. They only did a few, but now computers. All right, and finally, we can numerically solve the model, which means numerically start out some initial conditions, project them forward over time. So for that, we use this ecosim. We give it some initial conditions, tell it how long to run, and then we're going to take the answer and store it in this SOL variable, and then we'll plot the solution. Okay. As expected, we start with them both rare. Species one, they both grow initially, two kind of peaks and then goes extinct, whereas one goes up to its carrying capacity, competitive exclusion. And this is just like superimposing that time dynamics on the phase plane. So this, yeah, I can't quite get on the same page. But anyways, this black trajectory here is the same as these two time series up here. So we can see we start off close to 0, 0, this unstable equilibrium point. We ran away from it and we kind of got sucked into this one and we ended up there. Okay. All right, so that's case one. I'm not going to do case two because it's the same thing. Here's the coexistence case. I'm just tweaking the parameters. I know that this will work. So now we have, well, let's get the picture so we can have that handy. Right, so now we have, okay, so now we have 4 equilibria. The trivial one, it's unstable. Species 1 by itself, it's unstable. Species 2 by itself, it's unstable. Finally, the coexistence equilibrium point at 2/3, 2/3. Finally, it's stable because these are both negative, right? So this is kind of doing the local stability analysis numerically now. This is doing the invasion analysis. We see these are both positive, so each species can invade the monoculture of the other. Phase plane puts it all together. And if we were to simulate it, then we see that, yeah, the two species go up and coexist and end up at the coexistence point. Yeah, Sarah?
Yeah, it's about the eigenvalue. So I understand that the sign matters, that they need to be both negative so that there is coexistence. But is there any importance in how different they are? For example, here it's -1 and -0.3. If the second species would have -0.1, would it have any importance or just into the representation of the coexistence?
Yeah,
more
no,
the
that's great.
pattern of it than the strength?
Yeah, that's a great question. So question is about the eigenvalues associated with this coexistence equilibrium point. And I didn't get into this, but each eigenvalue has a direction associated with it on this phase plane. That direction is given by the so-called eigenvector, which I didn't draw in here, but essentially the two eigenvectors at this coexistence point, one is going like this. So it's kind of like in the direction of total abundance, N1 plus N2. And the other eigenvector is going orthogonal to it in this case, and it's kind of going in the direction of relative abundance. So this -1 eigenvalue is sort of the stability in the direction of total abundance. And it's pretty stable along those directions. So the more negative you are, the more stable an equilibrium is. Perturbations will die off faster in this direction. The -0.333 here, the -1/3, that's kind of looking at the stability in this direction of relative abundance, kind of going up, left versus down, right. And so that's also stable, right? It's also negative, so good, stable equilibrium point. But it's a little bit less stable in this direction. So like if you perturb this way, if you were to like tweak the relative abundance of the species, then like it's gonna be a little bit slower to get back to the equilibrium. Yeah, so in this case, these two, the two eigenvalues for every equilibrium point, they're not like assigned to like species in particular. It's more like there's some characteristic directions of this vector field, and the directions change depending on which equilibrium point you're talking about. So yeah, so that's that. And we'll see something interesting with those things in our next example. Yeah, Clara?
Yeah, while you're clarifying this, and I don't know if this is just taking it too out of the direction of where you wanted to take it, but can you also explain why the eigenvalues, the positive eigenvalues match the parameters that you derived in the invasion analysis?
Yeah, they match. So again, yeah, right? It's like a big coincidence here, like this 0.5 eigenvalue and this 0.5 invasion rate. What the heck? And so it's not an accident. It's basically because the eigenvector that's assigned to this 0.5 eigenvalue at this boundary equilibrium is pointing straight up. So it's totally in the direction of N2 invading, and therefore it's the same as the invasion rate. Yeah, so the invasion analysis is basically a shortcut, on doing the relevant part of the stability analysis. So yeah, it's a good observation.
Oh, thank you.
All right, so now let's just do this boundary control case because it'll be interesting to contrast with the stable coexistence. So in this case, again, we have 4 equilibria, but now these boundary equilibria are both stable, -1, -1, -1. And this coexistence point here is now unstable because we've got a -1 still, but now we got a positive eigenvalue. So again, just based on like this isn't always gonna be the case, but this is such a nice symmetric example, I can say this is literally true. The stable, the -1, that's in this direction of total abundance. And so you can see, like, based on the way these arrows are pointing to and away from this equilibrium point, it's kind of got like one stable direction, but it's got this unstable direction, which is the relative abundance. And so that corresponds to the +1/3 eigenvalue. And that's basically saying that, yep, we're going to end up with some abundance, some species, biomass in this ecosystem. But like which species it's going to be, we can't really say. That's going to depend on initial conditions. And so this particular kind of equilibrium point here, let me zoom in on it as much as I can here. This particular kind where you have like one stable direction and one unstable direction, that's technically what we call a saddle point. Because you can imagine like a horse saddle, right? And you're like rolling a ball on it, right? It's got like one stable direction, but then it's going to fall off the side. Yeah, so it's kind of like putting it all together, the local stability analysis as well as the phase plane. Yeah, Sarah?
So I understand that if the arrows on this exact graph points toward each other, then it is linked to total abundance, and when it's away from each other, it's relative abundance. And maybe it's trivial or supposedly no, but how do we know that? Because before you explained it, I was not aware. Like, what's the?
Yeah, I'm just telling
explanation?
you
Oh, yeah.
something. I'm just telling you something that I happen to know about this particularly supersymmetric, nice version of Lotka-Volterra. If we really want to know what direction they're pointing, you can calculate the eigenvectors as well, and that will tell you which direction they are. Yeah, so it's just kind of like, because this particular one is so nice and symmetric that it like points in the direction of total abundance versus relative abundance, has a nice intuitive feel. But if I was to like perturb this a little bit, make it a little bit like crooked, it wouldn't necessarily have that exact interpretation.
Okay, thanks.
So I can run a couple, now we're gonna run 2 simulations and just start them with like different initial conditions. So first one, species 1 gets a little head start, second one, species 2 gets a little head start. And you can see like, yep, we ended up with different outcomes. And if we were to superimpose those 2 trajectories on here, it's like, yeah, we split off and ended up at one or the other stable equilibrium point. And finally, we got to see the case of neutrality. And unfortunately, my picture a little bit wonky. I don't know why it's putting dots there, because this should all be like a whole bunch of neutrally stable equilibria. But we see at least finding the equilibria, it finds that it says, yeah, there's a line of equilibria. It's n2 equals n1 minus n1. That's the line. And it even assigns like eigenvalues to that line, of which one is -1, that's the stable total abundance. And then the 0 is kind of the neutral stability along the basic lines. That's kind of a miracle that it works out like that. Invasion rates are 0. Everything is kind of like neutral here. And finally, if we run 2 different simulations, we just end up going to a different point on here, but we could run more simulations, we'll end up going to another point. This is like neutral theory is whatever, in this case, whatever initial relative abundance we put in is just kind of frozen for all time. So it's weird. All right. Any last questions on this? Like kind of like putting it through its paces, numerical examples? And I'll figure out some way to like send these around.
So Chris, maybe let me ask about like the neutral theory example. That's like, so let's say you get to, okay, so one of the species isn't just automatically excluded. Like it'll just have a different relative abundance on the initial, and then a perturbation, I guess. Yeah, it just might move it a little bit.
Yeah. Yeah. So it's pretty weird. I mean, it's basically like an, you know, it's like a ball on a perfectly flat landscape, and like you pick up the ball, move it to the side, it'll stay where it is. You know, Hubble's neutral theory added some other things like stochasticity that would actually get it to like move around.
Right.
All right, well, I'll send this stuff around. So I got a little bit more PowerPoint I want to wrap up with, and I think we're actually gonna, I think timing is pretty good here. Okay, so that was the mathematical examples. All right, so now let's just take a quick tour through phase planes, and we're just going to vary the strength of competition. I'm just going to make it so that the species are otherwise symmetric in this particular example, so equal intra-specific competition coefficients. Okay, so this is our picture, remember, for stable coexistence. So now the inter-specific competition coefficients are less than the intra. That's kind of like the recipe for coexistence, is when you compete more with yourself than the other guy. Here's an example where intra equals inter, and then we end up with this weird neutral thing. If we go beyond that, if we make inter-specific competition stronger than intra, then we end up with founder control, because whoever gets in there first is going to like ruin it for the other guy and keep him out. So this is kind of like our tour through strength of competition. Now we can go to the opposite extreme. If the inter-specific competition coefficients are 0, well, these species don't even interact. right? So their isoclines are perpendicular to each other, and there's kind of independent logistic equations like we started out with at the very beginning. But we can actually, like, what the heck, let's go further. Let's go beyond non-interacting from competition. Let's move into mutualism. Let's make these competition coefficients negative. Yeah, Matt?
Can I, so like, so now I'm just kind of trying to imagine the K formulation here. Would the species go to like half of their relative, like assuming like carrying capacity was set, like would they each go to like half the total? Or no?
I mean, it would be the same. Like if they don't interact, right? They don't interact, so everyone just goes to their carrying capacity.
Right. But I guess, yeah. Okay, but if you implicitly assume that there is one carrying capacity, then I guess you're also just assuming that there is competition, that they will reduce each other's relative.
Yeah, that's more,
Okay,
that's gonna
gotcha.
be more like this case of like, total niche overlap or
okay.
neutral theory. Now you see that basically
Got it,
adds
okay.
up. So now the total abundance, either you got like one of this guy, you have one of that guy, or you have 0.5,
Yeah.
0.5, it all adds up to the same.
Okay, cool, thanks.
All right, so now I'm gonna push it into mutualism. And this is already done in 1935 by Gauss and Witt. But anyways, it just works, right? So now the isoclines are kind of angled out a different direction. And you see that this weak mutualism case, they still stably coexist. And in fact, their abundance when you put them together is higher than when they were by themselves because they're helping each other out because it's mutualism. So Lotka-Volterra, mutualism, just make competition negative. But don't go too far, because if you go too far and make mutualism so strong that those isoclines don't intersect anymore, then there's this kind of like runway, this path that just leads off to infinity of both species, and they blow up. Technically, they reach infinity in finite time. Not a good model of strong mutualism. But anyway, just tossing that out there. And then there are like ways to fix it, right? So any question on this kind of like tour of Lotka-Volterra, strength of competition or mutualism?
Yeah, what is the limit of the value for a alpha, for the alpha to not reach this divergent solution?
Yeah, I don't know off the top of my head, but I'm pretty sure it's like, if we go back to this expression for the equilibrium, it just makes sure that that denominator doesn't go negative, right? So I bet that's probably the condition, right? Just take this denominator and check to make sure that it's positive, not negative. That's probably how you know you've gone too far.
Sure, thank you.
Yeah, and people
I guess,
worry about that, but not too much.
yeah, I guess I didn't realize before. So with weak mutualism, you can get well, I guess, yeah, it doesn't blow up.
Yeah, it's not a total disaster.
And they will get coexist. Okay.
Yeah,
okay.
it's not that bad.
Yeah.
I think people have the impression that Lotka-Volterra mutualism is inherently like going to blow up, but only in certain cases.
Okay, that was my impression. Thanks for correcting that.
All right, so just to wrap up, I'm going to tie this into this like so-called modern coexistence theory that a lot of people talk about these days, because it took me a while to figure out even what that's about. So it's based on the work of Peter Chesson. This 2000 is like super influential review. I think he has some more recent papers that are a little bit easier, more pedagogical. There are two different strains actually of this modern coexistence theory. That are kind of similar but different. There's a Lotka-Volterra based one and one based on invasion rates. We're going to start off today. We're just going to talk about the Lotka-Volterra one. And there are a lot of different ideas that are kind of like thrown in here. But one of the ideas that super popular because it's nice, makes you feel good, intuitive understanding of competition is it's a way to think about coexistence and to partition it into two kinds of things, what we're going to call niche differences, what we're going to call fitness differences. And I'll show you in a second just what that means here. And if you want to read more, there's this recent overview by Juri Barabas and colleagues. Although I think it's mostly about the invasion version. Okay, so what is this? Oh, I was gonna like add some slides so I could just dish this out bit by bit. Now you have to look at it all at once. So here's the idea. We're gonna start out, it's based on the mutual invasion criteria, right? And so we have in our hands, we have expressions for the invasion rate of each species growing into a monoculture of the other. So this lambda 1, this lambda 2. And therefore coexistence, if each species can invade a monoculture of the other, that's this first line of expressions there, 2 expressions. But we want to stick them together. We want to bolt them together. So we see each one kind of depends on R1 over R2. So let's just like rearrange it and isolate the R1 over R2 and stick it in the middle. So this is equivalent. It's just a shell game. We're just moving around the shells here. And this one's not perfect either. I mean, it's true, but it's not exactly where we want to go. So the final step here is we want to make it kind of symmetric. And so a little bit convoluted, but if we do, some appropriate factoring out here, we can rearrange it so that on the outside, we've got this square root of alpha 1, alpha 2 divided by alpha 1, alpha 2. And then this thing over here on the left is the same thing, but just the reciprocal, just flipped. And so now, finally, this is it. We're going to take this thing on the outside, the little bumpers there, and call that rho, which is going to be our measure of niche overlap. And then this thing in the middle we'll call delta and call that the fitness difference between the 2 species. And so then the idea, when you finally get down to it, is that species coexist if their fitness differences are small enough that they fit between the niche overlap and 1 over the niche overlap. So that's the concept. I've had some issues with this thing in the middle, the so-called fitness, so-called difference. Well, it's not a difference, it's a ratio here. But that's okay. Anyway, the paper we'll read for next week is I'm kind of like riffing on this a little bit with my former student Ravi and postdoc Toma. So you can read more about it over the next week. But this is basically what it's about. And then we can look at this graphically and we'll see this like famous figure that whenever you see people talking about coexistence, modern coexistence theory, you see this figure. So it's plotting the outcome of competition as a function of the niche overlap versus the fitness difference between species. And this is just plotting that inequality. And so what we see here is that the coexistence region, if species have similar, if there's little fitness difference, then coexistence region is pretty narrow. But then if we move to the left, there's less niche overlap between the species, more niche difference. Now the coexistence region is getting wider. So you can tolerate more fitness difference because they're not competing so strongly. You can think of this x-axis as kind of like the strength of competition here. Finally, on this end, if they don't compete at all, if they have 0 niche overlap, then coexistence is automatic. This just kind of like opens up. Alternatively, if your fitness difference is a little bit too strong, then you get competitive exclusion. If you move to the right, if niche overlap is more than 1 or more than 100%, and it's not really intuitively clear what that even means. So I think we even made up a term in our paper called it, Elena made it up. What does she call it? Paper? No. I have to look and see what it was. It's some kind of like, beyond, more niche overlap than is physically possible. If that's the case, then instead of having a coexistence region, you have this region of founder control opening up. Okay. So that's I don't know, we'll see this again later on, I'm sure, and sure you've run into this thing before. This is basically the Lotka-Volterra version of the modern coexistence theory. Yeah, and the idea is that if you want species to coexist, you can do it 2 ways. Either you can have species with little inherent fitness difference. So you're like on this horizontal dashed line. That's called an equalizing mechanism. Or another way to make species coexist is decrease their niche overlap. That's called a stabilizing mechanism. That's lingo.
Sorry, can you say that again? What is the first one called?
All right, so the first one, if you're like moving towards the center of this coexistence region so that the fitness difference is 1, it's really a fitness ratio. That's called an equalizing mechanism because they're both kind of like inherently equally good competitors. And then the stabilizing one is move to the left here so that you don't have a lot of competition, decrease the strength of competition. Yeah, Nina?
So is this an attempt to sort of reconcile neutral theory and sort of classical? Like if you're moving to the left, are you basically becoming more neutral? Because there's
Yeah, thanks for pointing that out. That's a good point. And speaking of points, right there in the epicenter, little belly button there, where you have total niche overlap and fitness ratio is 1, that is indeed, right there is like the case 0. That's the neutral case right there at this intersection where it all comes together. So Hubble's neutral theory is right here.
Okay.
And if you move a little bit to the left, you can think of it as kind of nearly neutral, right? They compete a lot, but not 100%. So then, you see like the coexistence bandwidth, the region of coexistence is pretty narrow. You got to really fine tune the fitness differences. So yeah, that's how it relates to the neutral theory. I should label that.
Okay. Thank you.
All right, so now I just got to wrap up because we only got 1 minute here. So set the stage for the rest of the seminar here. Lotka-Volterra competition, pros and cons. So I'm not dogmatic. Lotka-Volterra competition's been good for 100 years. We're going to keep on using it. It's analytically tractable. We got our graphical phase plane analysis. It showed us these outcomes of competition, including some that we probably wouldn't think of without the model, like founder control. And it's phenomenological. That's actually a pro. That just means that like if you need a model of competition, you don't want to get too detailed with how they compete, use Lotka-Volterra. It's the simplest thing. On the cons, it's linear in competitive effects. So the isoclines are linear. But most of the problems with Lotka-Volterra competition have to do with the parameters. So here they are. They have no physical meaning. You can't you're never going to find like a competition coefficient in some species genome, okay? If you want to go out and measure it, you have to actually put them into competition, see what happens, and then you measure that's how you measure the competition coefficient. It's unclear how all these parameters depend on environmental gradients. It's all about like what happens in this particular community, but what happens if you like dump in more nitrogen? What's going to happen? Lotka-Volterra doesn't tell you anything about it. Cursive dimensionality, the number of parameters, those competition coefficients is like n squared. So like the more species you got, it gets harder and harder to measure all the competition coefficients. And finally, it's just like they're all kind of independent of each other in the model. So how do they relate to each other? What's like the right universe of competition coefficients and carrying capacities? It's not clear. So these are the issues. And as we'll see, starting next week, resource competition theory will come in and fix all those problems under the cons. So thanks, y'all. I'll send a reading. Oh no. I'll send a reading around for next week, and then we'll do that for the first part, and then we'll start talking about resource competition finally next week. All right. See y'all.
Thanks, Chris.
Yep. Bye.
Thanks. Bye.